Welcome to the lecture on system characterized by a difference equation using Fourier transform through the course signals and system. This topic is very important for understanding digital filters and signal processing systems. A difference equation mathematically represents a discrete time system. It relates the present output to past outputs and present or past inputs. In general, the difference equation is written as, that is, summation ak into y of n minus k equal to summation of bm into x of n minus m. That is, output terms on left side, input terms on the right side. This form is commonly used to model digital system. Why we use Fourier transform? That is, solving difference equation directly in the time domain can be complex. So we are using Fourier transform simplifies the analysis by converting time shifts into multiplication by exponential terms. Using DTFT, convolution becomes multiplication, difference equation become algebraic equation, frequency characteristic of the systems can be clearly analyzed. See, important DTFT property here we are using to analyze the system, that is f of x of n minus k equal to written as, when we are applying the Fourier transform for time shifting equation, difference equation here, that is equal to e power minus j omega into k into capital X of e power j omega. So the difference equation, this is the difference equation become, this is the right hand side represent the algebraic equation in frequency domain. So the frequency response of a discrete time system tells us how the system modifies different frequency components of the input signal. It is defined as capital H of e power j omega equal to capital Y of e power j omega divided by capital X of e power j omega. Once we know the frequency response, we completely understand the system behavior. Let us consider an example discrete time LTA system described by difference equation. Here difference equation identified from the given equation, that is y of n minus 0.5 y of n minus 1. This is a first order digital system. So here n represent discrete time. Once here d of y, d of t divided by dxt means, that is comes under differential equation. Instead here we are following y of n and y of n minus 1, that is named as difference equation. From this system we have to find frequency response, impulse response and output response. So once we have to find all the concept from the given system, in this system we are going to apply, first step is to apply the DTFT logic on both sides. So once we are applying the DTFT to both sides, that is capital F of y of n minus 0.5 f of y of n minus 1 equal to f of small x of n. Using DTFT property, we can get like this. Thus, difference equation converted into algebraic equation using this property. That is capital Y of e power j omega. It's a small y of n is written as capital Y of e power j omega. So the small y of n minus 1 written as e power minus j omega into capital Y of j omega. So small x of n written as capital X of e power j omega. So once we are getting the capital, we are applying the DTFT on both sides. Then after that we can factor, take a common term of y of e power j omega from this equation. We can take common term capital Y of e power j omega. Once we are taking common term here, our equation comes like this. That is 1 y of e power j omega into 1 minus 0.5 e power minus j omega equal to capital X of e power j omega. From this equation, we are able to find frequency response. Already we know the frequency response equation. Capital H of e power j omega equal to capital Y of e power j omega divided by capital X of e power j omega. That is equal to, that is this term x of j omega comes into left hand side, the remaining terms comes to the right hand side. That is, we can modify our equation like this. That is y divided by x equal to 1 divided by 1 minus 0.5 e power minus j omega. This is the frequency response of the given system. So let us move to another example. So where we apply the same DTFT procedure to a higher order system. Higher order system means that in the previous sums we have only y of n minus 1. But in this system has y of up to y of n minus 2. This is the second order equation. So in the similar way, here we are calculating the concept of find the concept of frequency response, impulse response, and system output for the input. Here the given input is small x of n equal to 1 by 4 whole power n into u of n. So from this system, given system, we have to find capital H, small h of n, then y of n. Let us discuss one by one. So before that, these steps are to follow the to find the concept of DTFT solving flow. So before solving the full problem, then remember this standard DTFT problem solving flow. First step, to apply DTFT on both sides to find frequency response, that is capital H of e power j omega, factorize if needed, then follow partial fraction expansion, then find impulse response, then apply DTFT for input signal, then find output spectrum, that is capital Y of j omega e power j omega. From this capital Y j e power j omega, take inverse DTFT, then find output response of the given system. So let us discuss one by one. So from the given problem, that is capital the small y of n minus 1 by 6 y of n minus 1 minus 1 by 6 y of n minus 2 equal to x of n. Here we apply DTFT logic 2 on both sides. So we can get thing like this. That is capital Y of e power j omega minus 1 by 6 e power minus j omega into y of e power j omega minus 1 by 6 e power minus 2 omega into y of e power j omega equal to capital X of e power j omega. Using this property, we apply the DTFT logic on both sides. Finally, we can get the difference equation converted into or transformed into algebraic equation. Through this equation, we can find the frequency response and impulse response and output response of the given input. So here we can take common term y of, in the left hand side we can take common term capital Y of e power j omega into 1 minus 1 by 6 into e power minus j omega minus 1 by 6 into e power minus j 2 omega, that is equal to capital E power j omega. Once we are taking this term, we can find frequency response of the given system. Frequency response of the given system already we know. To know the equation, to find capital H of e power j omega equal to y into e power j omega divided by capital X of e power j omega, that is equal to 1 divided by, that is equal to, this term comes this side in the numerator term, then remaining terms shifted to transform to the right hand side equation. That is comes like this. That is 1 divided by 1 minus 1 by 6 e power minus j omega minus 1 by 6 e power minus 2 omega. So in this equation we have to apply the factorization. So that is this terms we need to factorize this term. That means we can take factorization form. Here is minus 1 by 2 comma plus 1 by 3. Once we are multiply the both value, minus 1 by 2 into minus 1 by 2 into 1 by 3 equal to minus 1 by 6. This minus 1 by 6. Suppose we adding both terms, that is minus 1 by 2 plus 1 by 3, we get that is minus 1 by 6. This is the factorization logic. Already we know that logic. Applying that factorization logic in this term, finally we can return as that equation like this. That is capital H of e power j omega equal to 1 divided by 1 minus 1 by 2 e power j omega into 1 plus 1 by 3 e power minus j omega. After finding this concept, we can apply the partial fraction expansion. Assume this term like this. That is a divided by 1 minus 1 by 2 e power minus j omega plus b divided by 1 plus 1 by 3 e power minus j omega. Solving this constant value a and b using partial fraction logic. So here we take LCM term, that is 1 minus 1 by 2 e power minus j omega into 1 plus 1 by 3 e power minus j omega equal to a into this term, b into this term. So the term written like this. That is 1 equal to a into 1 plus 1 by 3 e power minus j omega plus b into 1 minus 1 by 2 e power minus j omega. This is the this terms written like this. From this concept we have to find, we are able to find a value and b value. From this one we have to cancel the term either a or b value while substituting through the substituting value of e power minus j omega. Then only we are able to find the a constant value and b constant value. First we have to find a constant value a. So during that time we have to cancel the b term. So at that time we have to substitute e power minus j omega equal to 2. Once we had substitute this value in this equation, the b term will be cancelled. So we can find the a value. Once we substituting e power minus j omega equal to 2, finally we can get a equal to 3 by 5. Similarly, we can calculate the value of b value. So once we can skin this to find b value, we have to substitute e power minus j omega equal to minus 3. Then only we are able to find the b constant value equal to 2 by 5. Like we have to find, where we can substitute a and b value in this equation. A and b value. So once we are here substitute e power minus j omega equal to minus 3, at the time this term will be cancelled. Once we are substituting minus 3 here. So during that time we are able to find b value equal to 2 by 5. So once we find the value of a and b, substituting that value in this equation, that is this equation. So here what is the a value? 3 by, what is the a value? 3 by 5. What is the a value? 3 by 5. What is the b value? 2 by 5. So once we are getting this value, we have to apply inverse Fourier transform to find impulse response. So already we know this the standard formula, that is once we are applying the inverse Fourier logic for this equation, we can get this standard signal a power n into u of n. Instead the a power n, here we follow 1 by 2 power n. Here in this term minus 1 by 3 whole power n. That is from this equation, we follow the standard DTFT logic, the inverse DTFT logic. There we can return as like this. That is 3 by 5 into 1 by 2 whole power n into u of n plus 2 by 5 minus 1 by 3 whole power n into u of n. This is the impulse response of the given system. In this step, after that, in this step, we compute DTFT of the given input signal. So, given input signal equal to small x of n equal to 1 by 4 whole power n into u of n. Once we are applying DTFT logic, we can convert it into algebraic notation, that is capital X of e power j omega equal to summation of 1 by 4 e power minus j omega 1 by 4 e power j omega whole power n equal to, that is 1 divided by 1 minus 1 by 4 e power j omega. After getting the capital X of e power j omega, we are substituting the value in this output spectrum equation, that is y capital Y e power j omega equal to h of e power j omega into capital X of e power j omega. So substituting h of e power j omega value here, then x of e power j omega value here. So here also you can apply the partial fraction logic, that is capital Y of e power j omega equal to a divided by this term, b divided by this term plus c divided by this term. So here also we have to find constant value of a, b, c when applying the partial fraction. So already we know the concept of partial fraction. Through this concept we have to find a value. So in this a value, to find the a value, we have to need to cancel b term and c term once we are substituting e power j omega equal to 2. Here we can substitute 2 value here. Here also e power j omega 2 cancel. So automatically this term comes 0. This term comes 0. That time we can find the a value, that is equal to 6 by 5. Similarly, we can find constant value b once we are substituting e power minus j omega equal to minus 3 in this the previous equation. The b equal to 8 by 35. Then next we can find the constant value c, that is equal to minus 3 by 7. Finally, we can substitute all the value in this our output spectrum equation, that is capital Y into e power j omega equal to a value is 6 by 5 divided by 1 by 1 minus 1 by 2 e power j omega minus j omega plus 8 by 35. This is a b value. This is minus 3 by 7 is the c value. This is the output spectrum expression. Then after that, we can apply the inverse DTFT. So once we are applying the inverse DTFT, that is 1 divided by 1 minus, this is comes a into e power minus j omega written as that is 1 by 1 a power n into u of n. So instead in a we can write 1 by 2 whole power n into u of n. This is the concept of once we are applying inverse DTFT in our output spectrum response, we can finally get output response y of, that is capital Y of e power j omega written as, once we are applying the inverse DTFT, small y of n, that is equal to 6 by 5 into 1 by 2 power 1 by n into u of n plus 8 by 35 into minus 1 by 3 whole power n into u of n minus 3 by 7 1 by 4 whole power n into u of n. This output represents zero state response of the system. The summary of this lecture is, so the complete DTFT based analysis follows this sequence: difference equation, then comes into frequency response, from frequency response to find impulse response, from the impulse response to find output response. This method is systematic, exam oriented and very powerful in digital signal analysis. Thank you.